So the message was from NetConf is that it's going to be easy to display. So we tried different VGA cables, nothing worked. We tried a Linux machine, it didn't work either. And now we're back to a Windows machine, and that actually works. So I'm not sure what that tells me. Anyway, this is a tutorial on NetConf and Yang. I have a number of slides prepared, so on the lower corner it says 90. Don't be afraid, I'm not going to go necessarily through all the slides. In fact, if you have questions, I'd like to ask you, invite you to ask the question as you go, rather than waiting. Because commonly, if you're very much involved in the subject technology, giving a tutorial isn't really easy because you're way too much in the technology to give a good tutorial. So trying to step away and trying to explain things for people who haven't been working on this for 10 years is usually a difficult, not so easy thing. Now this is Bert Weinman. We're talking about the network management protocol suite. This is the bowl of network management protocol standards. The only message you should get from the slide is that there's lots of them. And quite a number actually have an IETF label on it. And NetConf Yang is just another piece in the bowl of network management standards. And what I want to do in the tutorial first is try to give some background information why NetConf Yang is there. So what was the reason we actually created. And I'm going through a little bit of technical details, how does the protocol work, how does data modeling work in the context of NetConf and Yang. And then go a little bit about talking about what's implementation status today and where things might go in the future. So the menu of today is NetConf, and if you read the abstract of the protocol definition, and it says exactly the sentence. So it's a network configuration protocol, provides mechanisms to install, manipulate, and delete configuration of network devices. So the key word here which pops up multiple times is configuration. And so the target of NetConf is to support device configuration and not necessarily monitoring or discovery or any sort of little thing. Now when NetConf was created, the directive that was given by the IETF or the ISP or whatever was to do a protocol first and not do any data modeling language for it. Only when the protocol activity succeeds, then we can go on and actually think about data modeling. So Yang came later, you put on the block, and that's the data modeling that's supporting everything that NetConf has to provide. It provides NAT configuration, but it's also notifications, because notifications got actually added to NetConf as another feature to report events. Okay, what I'm going to do is talk about configuration management and the protocol and other stuff we do. So if people run networks, there are essentially two types of extreme ways on how you can run a network. This is the first one. I call it the network as the record. Essentially what happens here is you have some sort of a human who is in the center of the figure, and the human absorbs information coming from the network about topologies, or what's connected where, what's the cabling situation, and so forth. It receives policy information, so which part of the network could be accessible to whom and when, under which conditions, and so forth. There are system management services that need to be provided in the network, and then there's network status and performance information, and all that is kind of done to a human or a bunch of humans that actually go into the network and start making changes. And what's happening is that the human or some tools working with the human is creating device configurations interactively or by ad hoc tools. And if things are well organized, then people usually collect those device configurations periodically, store it into a version control system, such that it's possible to answer questions like, why did my service stop working this night or yesterday, So can I go in and see what changed at that time, because it often explains why something doesn't work. Okay. This used to be popular, especially off of smaller networks, enterprise networks that kind of set up working this way. It has a big disadvantage, and that's the humans. So humans make mistakes. Humans sometimes go on vacation and other things like that. And if you remove the human, the central point from the system, then the system still functions, but once it stops functioning, you have a problem. The other approach in that configuration is to generate everything approach. There's actually a document after 31 and 39 that talks about kind of the setup. And the idea here essentially is that the device configuration is not really touched by humans anymore, but instead you have a network-wide configuration database that defines how your network runs. And everything actually goes to a centralized system, and the centralized system generates the configuration that goes to the network devices. So the point is humans don't touch devices, but everything goes to a centralized system that allows you to implement additional checks, sanity checks, that people don't fill up the whole network if they're making stupid mistakes. Okay. Some networks in the wild actually are in between those two extremes, so some of that runs this way, some of that runs the old sky way of humans touching everything, so the world is really much more colorful than these two models suggest. Now looking into that figure, where does NETCONF come into play? Essentially, the time part when NETCONF was created was to be an interface, standard interface to do device configuration. So allowing to push config changes to devices in an automated way and making it simple. So rather than scripting CLIs that might change arbitrarily, being released indefinitely across vendors, to have a standard way of actually switching configuration down to a device to the configuration and putting in a device. That's the prime target of the work, do something on this stage. Now, the whole thing started about 10 years ago. In 2002, there was an IED-invited workshop on network management and things that work and things that don't work. So the IED invited people, device vendors, protocol developers, some academics have been there. And the idea was to figure out what works given the set of protocols that the IETF has and what is missing. And one of the things that is very clear is we don't really have a standard way of configuring boxes. As part of the IED workshop, a number of requirements were identified. And I'm going to go through them quickly one by one. There's the document up to 3535. This is the workshop report. If you want to read about more details, you can find stuff there. The first requirement says the configuration management protocol must be able to distinguish between configuration state and operational state. It's funny that some people were surprised by this state, but it's very essential that you know whether an IP address is there because it was statically configured to be there, or whether the IP address is there because the HTTP shard, you may use this IP address for a while, but tomorrow you might use it. It's important to understand this routing table entry is statically configured and exists because some system or some human configured it there to be there, or whether it's a routing table entry that came from some routing protocol and is volatile in nature. It's important to distinguish. And it's kind of funny that everything the IETF did until 2001 was kind of ignoring it. So there are lots of SNMP-based data models that don't really distinguish this kind of thing. So it's actually impossible to write simple SNMP-based applications that pulls out configuration data because it's all messed up with operational state data. So even doing a very basic operation doesn't really work. The second requirement talks about concurrency support. Our configuration protocol must support primitives to prevent errors due to concurrent configuration changes. Configurations on boxes are not changed by one person or one application at a time. If you look at bigger boxes, then there's actually multiple things going on, multiple applications provisioning different parts of the configuration that sit on the device. And so you have to be careful to support that properly. Even if a box is just touched by humans, you have to be careful to make sure that those humans coordinate somehow. Right? It's not useful. Someone does an IP renumbering and someone else does a different IP renumbering. That's usually not going to work out very well. Yeah. So very simple. There needs to be some concurrency support in the protocol. Another thing that should be relatively clear for networking people is that sometimes you want to make configuration changes not just for a single box, but for a bunch of boxes. And the configuration needs to be consistent after applying it. So in other words, the configuration needs to apply to all the boxes together or to none of them. Typical example is again the numbering. You want to change the number, the addresses that you use in the network. If you do that, one device after the other device, you might run into a situation that part of the network isn't reachable anymore, while the other part might still be reachable to some extent. You might just have complete new transaction. So what you really want is a way of provisioning all the changes, and then say, do it, make it so, and have built-in mechanisms that allow you to go back to a changed state. To go back into a well-defined state, and not in the middle of a transaction which is totally undefined, and then you have to go in and fix all the boxes that have an inconsistent configuration. So it's important to have a notion of transaction supported process multiple devices. Another thing that's likely very clear to many operational people, you like to distinguish between multiple configurations. You might have a backup configuration that is most known to work. You might have something more fancy that you're working on. You might have configurations that you use during daytime and during weekends and so on. So it's important to distinguish between them and not just believe there's only one configuration on the device. And once you distinguish multiple configurations, you want to distinguish between distributing the configuration and activating it. So you might actually distribute context without activating it, and have another operation that allows to activate and say, well, now from now on, please use a different configuration. And it's just cost savings of not just pushing the configuration again, it's storing it locally that makes regular changes go fast, and it allows the implementation that is optimizing the device behavior to actually have additional information associated with the configuration, so it can actually change over faster. So it's not just getting a totally new configuration, but it's getting a configuration that you already know. So it might happen probably reflected to make it into a process. Another requirement, consistency of configuration. Data needs to be clear. You configure something. Sometimes you configure something because it should always be in that configuration. Sometimes you change something, but you really don't want to have it when the device is used because that's kind of an experiment that you're doing, and if in the worst case you swap the cable and plug it back, then the device should have forgotten everything that you did to it. So it's important to have the notion of what is the consistency of the configuration change that I do. Another requirement coming out of the IED workshop that it's important to track configuration change events. So if you're running a larger group of people with touch devices or multiple applications with touch devices, it's important to track what's happening to your configuration change. So you want to have a lot of every configuration change, such that you can go in, if you can monitor what's happening, you can go in, if my customer starts calling, can I check what configuration changes took place just before it starts picking up the phone? These kind of things need to be supported. Requirement 8. Again, very simple, very basic. You need to have a read, dump the whole configuration, and read store. So that's very basic again. Surprising that some people, they're surprised that some protocols don't give it to you. So apparently, that's one of the basic operations that you need. Requirement 9, whatever you do, should send a tool set. So use data formats and encodings and tools that allow operators to use standard tool sets to manipulate data and to build hard tools of their own to automate part of their processes. So stay away from an encoding where people don't usually have the tools or don't have the knowledge to deal with that feature. Now, if you look at a protocol like SNMP, which is out there since the late 80s, and look at these 9 requirements, then it says pretty much all of them except 2 which is, you can argue, but probably supported partially. So that's really a bad record. The part of the work that happened after the IED workshop was that people said, well, probably that we're trying to do something about it and create a protocol that actually can be used for configuration. And it's no wonder that NetConf now gets lots of process there because NetConf took advantage of the outcome of the workshop and tried to address all those requirements. The things that are marked in square brackets are kind of optional features within NetConf. So not every NetConf implementation has to have it. So as we will see later on, NetConf has a bunch of features. That's indicated there with the square bracket. Okay, so that was the outcome of the workshop, and here's the actual timeline of the whole work that took place. So from 2002, it took a while. Well, in terms of IETF speed, it was still pretty well doing, right? So about 1 year later, actually the working group got established. And the report came out 1 year later, kind of as well, so that's the kind of thing it takes to write a report, so something like that. The working group did work hard on it, and in December 2006, the specification NetConf 1.0 popped out. So that's not really too bad. And then in 2007, people started to meet and work together, coming up with ideas on how to do data modeling for NetConf. And in 2008, that led to the NetConf working group starting work on some data modeling language, and 2010 October Yang 1.0 was published. So that's again a promising new path on IETF working distribution. In June 2011, NetConf 1.1 got published. Like any new protocol, you usually want people to start implementing it, start exchanging messages between each other and figure out that, yeah, that's not totally well described here and that's not totally clear over there. And so the NetConf people would sit down and work out all the details and revise the NetConf 1.0 specification in NetConf 1.1. Another thing that happened with NetConf 1.1 is specified using Yang, which didn't exist before. So it's actually using Yang to specify how much to do. So now there's a tutorial, 2012, about 10 years later, since the very beginning from the IED workshop. There's now a tutorial at the IETF. The NetConf working group is working on some core data models. I'm going to talk a little bit about that later as well. And we hope that we got things to some extent right and see lots of more configuration data models as we come along in the future. Okay, so that's the short background. And now my intention is to go into a little bit of detail how the protocol actually works on the wire. So what's happening between the client and the server and the talk to each other. And later on, we can look at the data modeling languages where you can actually abstract from them. NetConf, RFC, quite a number of them meanwhile, and I don't know every RFC. So there are some additional RFCs that I believe are going to die, or they didn't make it into the list, but that's my personal judgment. That might die. But it's essentially transport. NetConf natively runs over SSH. They have been transport for other protocols like Beat, you know what Beat is? Yeah, so that's not the majority here, so that might die out. And so some of those transport networks are not on the slide. If you want to have introductory reading material in the form of an RFC, then clearly 6244 is your friend. Gives you kind of a motivation of why NetConf works the way it works, what kind of problems it comes with it. Now, NetConf, as I said before, is primarily an interface designed to work between a device and a configuration system. So the idea is you have a NetConf manager which runs applications of some sort that generate and maintain configuration state in the network, and it's embedding a NetConf client that's talking to a NetConf server that's sitting in your device. So here's a server, here's another server sitting in the device. The NetConf happens between those two entities. The server needs to interact with whatever the device has to do something. So if you push down an IP address, it needs to go into your operating system kernel or whatever your device has. And we just call that an instrumentation here. So that's fairly device specific. Now, one of the things which NetConf also does pretty well is that it allows you to also run a client within the server, within the device itself. And on top of that client, you can actually provide a CLI. So there are devices out there where if you go to the native CLI on the device, what's happening really is that you're typing something that's at the end just the client talking to the internal NetConf server. Why is that useful thing? Well, it's just to make sure that whatever works over that interface works over that interface like this. So it makes the software architecture internally much simpler, and it gives the operator consistent data. Consistent interfaces and consistent data. With SNMP, you know that on some devices, the instrumentation from the SNMP world is pretty much detached from the instrumentation of the CLI world. Not necessarily, but some vendors will also go to common interface, but on some vendors that's actually pretty separate. And to pull out information, that's also something that was reported at the ID workshop, that the counters just don't align. So the CLI shows different counters than what you get from the network management side. That's not very great for people who like to use the counters to pass and so on. So that kind of works. It's not a feature of SAN, it's a feature of implementation. You can do something like this. But also works because you can do something like that. You can just run the whole CLI remotely. So you can have a program that's giving you a compatible CLI, and that's just talking to a NetConf server in your network, so you can actually remotely use your CLI if you happen to prefer talking to the box of your system. This is the NetConf 1.1 layering data that's in our C6231. And it says that NetConf itself has 4 layers. It has a transport layer, it's called a secure transport, because you assume every network needs to be secure to run NetConf over it. On top, and the default transport is SSH, as I said before. There's another document specifying how to run the left, in case you prefer dealing with access 509 certificates over whatever SSH public keys or whatever reason you might have if you prefer to over SSH. The other transport I mentioned, B, It's evidently the TLS security as well. There's a transfer for focus to the over TLS. And you can stack more on top of it if you want, and then the security goes in some of the data if you have to do. Now, once you have the session open, on the next layer you exchange messages between the NetConf client and the NetConf server. Most of the messages are just RPC invocations and RPC responses. And there's another message. And on top of the RPC mechanism, we invoke operations on devices. And that's where it's getting interesting, because there are a bunch of predefined operations that you can do, like giving your config, or here's the new config, or take your config and change it a little bit over here and over there to the new config. And these are standardized operations, but you can also add your own operations here. So it's rather powerful. It's not just limiting it to a bunch of operations that are predefined. It actually gives you the tools to add operations to it. So it's not on purpose limiting your imagination of what you can do. And then the top layer is the content layer, where you think about configuration data, so what's describing my config, how is my config structured, how do I use it. You don't think really about the operation, how you modify it anymore. You think about how to structure my data. Okay, another thing that needs to be introduced is the notion of a configuration data store. As I said, it's important to distinguish the consistency. If you make configuration changes, is it going to be something that's only valid until the device is used, or is it something that's being loaded when the next time the device is used, things like that. So the NetConf protocol has a notion of a running data store that's always present, and that's the configuration that's currently being used by your device. And that's always there because without configuration, the device is likely to be turned off. So once you turn on the device, it's going to load the configuration and it has a running configuration. And again, we're talking about configuration, we're not talking about operational state. So if you use the XPath, then the configuration is you use the XPath, not the IP addresses that the device uses. There's another configuration data store that's called the startup configuration data store, and that's the one that's loaded when the device initializes the next time. And that can be the same as the running configuration data store, the content-wise, but it might also be different. So you might provision something that's being loaded the next time the device is used, so that's different from what it's currently used. And optionally, you can have a candidate configuration data store, which is kind of a stretch buffer where you can make changes that aren't applied yet, but you can already make changes. You might validate the changes, so you can run a validation check, and the device says, yes, I believe I can actually do this for you, but it's not doing it. And if you want to think it's a good time not to do it, you can actually send an RPC call to say, now make it so. It's kind of a stretch buffer thing. Okay, that means in terms of changing configuration, you have different models of doing that. The first one is you have the running configuration data store, and you just make changes, and the operation that you use is called edit config. So you go in and say, I want to edit the running data store, and here's the change that I want to make. I want to assign this IP address, I want to use that IP address, and I want to add this button to it. If you use the candidate data model, then you can make those changes and the sequence of those changes if you want on a candidate data store. Nothing really happens on the device yet until you invoke the commit operation. At that point in time, the device will take the contents of the candidate data store and make it the running configuration of the device, if it works well. And the third model is you have a distinct startup configuration. So what you can do is you edit the running config using one of the other options there. So either directly or by committing the candidate to it. And then you can copy over the running config to be the next startup configuration you're going to use. Okay, so how does it look on the wire? Now remember, this was done 2002, we started talking about it, and the protocol was designed in subsequent years. So what was the encoding of that date? XML. ASM1 was the encoding of the date back in the 80s. People hate it. Let's see what happens to XML in 20 years or 20 years. Probably people hate it, but not so much so for like ASM1 and the encoding date. Anyway, that's what we have. So that company is XML on the wall. Remember, there's a secure transport, now you ship XML over. The first thing, when the client and the server start up and establish a secure channel between them, the first thing that a good protocol should do is say hello and exchange these wording and suitability information. And that's exactly what's happening here. That's the server hello message, so S colon the server does everything that the server says. And the server sends, after a session got established, a hello element, hello top level element, and inside we have a list of capabilities. So it says, I'm a server implementing NetConf, and by the way, I support NetConf base 1.1. I support the startup datastore capability. So not every device knows how the startup. So the startup datastore, but this device says, I am one of the devices that has this startup. And it says, I'm implementing the IETF interfaces data model. So it also announces the data models that are actually implemented on the device. If you read the details, it's not the same which data model it actually says, here's the revision data and so forth. You can actually link into other places where you can even get the different machines. Okay, that's the capability list. And at the end, the server says, this session got an ID, and by the way, that's full. Random. Full. It just gives you a handle to refer to this particular session. Most of the time you don't care. You will see one spot later on where this is useful. The client says hello as well. I don't have an extra slide for it because the client has left to announce. It just says I'm implementing NetConf 1.1. Oh great, we both do NetConf 1.1 and they're happy. If the client would say I'm NetConf 1.0, then the server might say, well, if it's you or NetConf 1.0, then I change my behavior so I can still talk to you. Okay, once the hello exchange is over, then most of the time, client and server exchange RPC. So there's an RPC element. Whenever you want to invoke a remote repeater call, the client calls the remote repeater on the server. You send an RPC message on RPC element. It has an attribute that's called the message ID. That's just the transaction only. It can actually do something else, I don't remember, but it's transaction only. And the next element says what kind of RPC you're invoking. So this is the common way we invoke the config to give you the config of, that's the first parameter, it's the running data set. So the source is the parameter of the get config and the value is the running data set. So relatively straightforward how things are encoded on the wire. If the server likes that particular request, it sends an RPC reply, which has the same message ID. So the server can actually send replies in different order if it really likes to do so. But in this case, it just sends a reply with the same 101 ID. And in the RPC reply, there's a data element which contains the config that you request. So that's the reply to this RPC. The data is the container that contains the output that's produced by the object. And so what's in here is the configuration of the Expath. Of course, that's not complete, because we all know stuff goes wrong. So here's another get request. And let's assume for whatever reason the get config can't be implemented. Then you get an RPC reply, but it doesn't contain data, but it instead contains an RPC error. And the RPC error is a bunch of elements that describe what went wrong. And so in this case, so the error happens on the RPC layer, and the error tag is missing attribute here. That's a well-known defined error that's somewhere in the protocol specification. There's a severity that isn't really very useful the way it's defined, so that doesn't matter here at the moment. And there's error input, which has additional information that can be passed back to the application. Yeah. So you send an RPC, you always get back an RPC reply. What it contains is either data, if the RPC is successful, or it contains RPC error elements detailing what went wrong. You come back to this later, because you will later see if you define new RPCs in the data model unit, you can actually specify what goes in here. Because sometimes what happens if you invoke an RPC and the failures you get are really specific to the definition of the RPC itself. Okay. So now client and server exchange RPCs back and forth, everything is great. So the question comes up, what are the operations that I can actually use? Because the set of predefined operations are part of NETCONF. So the first operation is called getConfig. And it takes two arguments. The source is simply the data store you want to get config from. So your running data store, or your startup data store, or your candidate data store. And because config can be really used on some devices, probably getting all config is not what we want, but we probably want to get something very specific. So you can provide a filter which allows you to say, well, I'm just interested in the interface configuration, or I'm just interested in the routing code. I'll talk later how you can syntactically write down the filter. There are actually two ways of doing it. One way is of giving a template XML document that kind of represents the data you're interested in. And the other alternative is you just write an XPath expression that leads to a node chart that you can use. The second operation called copy config, just copying a data store, the content of a data store into another data store. So if you want to copy the running config into the startup data store, you just do a copy config from running to startup. You can have the main data stores as an optional feature if you want to have, if your system supports storing configurations locally in files, you can actually say, well, I want to copy that into a file that I'm in. So the way you specify to provide a URL notation to it, and whatever URL format the device supports is going to be. If you have named configurations, sometimes want to delete them, so the delete config is straightforward. You can't delete the running data store, obviously, because you need to have a config, so deleting that isn't very useful. But if you have named configurations, so you have stored the configuration in the file you want to use. The most interesting configuration operation is called editConfig. And editConfig is essentially applying a hash to the data store you run editConfig on. So the first argument here is to call the data store. So I want to change the running config, or I want to change the candidate data store. And the changes that I want to make on the last argument here. So I might provide an XML snippet which says, Here is the new IP address that you want to add. Here is an IP address you want to delete, and that's the routing table entry that needs to be generated. Kind of a delta that you send to the device takes the running config, applies the delta, and creates a new version of the agent. The arguments in the middle, most of the time you like to ignore them, but some of them are really useful. The default operation says what you should do with the config that's provided here to be loaded or to be added or to be removed by default. We'll talk a little bit more about how this works when we look into the config itself. The error option allows you to control what should the server do if something goes wrong. Because there are different ways of reacting to failure. So if you send the device at this IP address and at this IP address, but for whatever reason the device says I can only have one of them, then what should the device do? Either fail the whole transaction, or say, well, at least those changes that make sense and I can see them. The other ones I report as failed, but I don't fail the whole transaction. You can have a long debate what's the right behavior, and the outcome was you can specify which behavior makes sense in your specific situation. The same for the test option. You can run validation tests. You can select whether they are being executed or not. So that's a way of setting this as well. All these arguments here in the middle have default, so if you don't care, then edit config really boils down to target and config as an argument. Okay, more operations. There's a lock operation. As that, there needs to be a way to deal with concurrent changes. And obviously, the way you deal with it is you have a kind of a locking mechanism. Now, this is a global lock on the data stream. So I can go into a device and I can say, I lock the running data stream. If the device grants the lock to me, anybody else who wants to make changes is not going to have anything to do. That's good, but not if I go out for lunch. So if you overlock on the data store, it could be 4. Because if you take the lock and it disappears, it just means other changes don't go into the device. There's an unlock operation. That's useful as well. There's a get operation, which is the extension of a get config such that it's not just returns the config, but all the state data that the device has as well. Coming back to my IP addresses, some of them are statically assigned, they are real config. Some of the IP addresses might be coming from the DHCP server. If I send a get config, I'm not going to see the IP addresses that come from the DHCP server because they're not config. Sometimes it's useful to see that. So you can send a get, and the get is going to return everything that the device knows. Up to the point that some vendors even don't want to implement it, because returning everything the device knows about can be really a lot. So after giving you everything on a backbone router, is likely going to take a lot of resources. Of course, you can specify a filter, makes it even more sensitive. You can narrow down what that's doing. Okay, what else do you want to do in a NetConf live? You want to close the session at some point in time, so you can both close session and have a proper shake hands for closing the session. Now, there's kill session as well. You know, that's the one that you need if someone took a lock and went out for long. Because if that happens, someone locked, nobody can make changes anymore. You have to take the comment on and clear up the situation. So there's a kill session, and now you provide a session ID here as an argument to kill session. And remember, the server initially gave out the session ID to every session, and that's the one that you have to put in here. Now, I'm not sure what the security people are doing, but if they were here, we would probably ask questions whether that's a useful thing to have. Operationally, that's very useful. Practically, not everybody really might have the solution to do that. That's actually a custom form model that allows you to set this up. So not everybody might be able to do that for someone else. Okay. Another standard operation is called discard changes. And that operation is resetting the candidate data store to some well-defined content. Remember, the candidate data store was the stretch buffer where you can do a bunch of edit context and at the end commit. Or decide, I don't want to commit. If you decide I don't want to commit, and you want to have a fresh candidate data store, you invoke discard changes because you have all the changes in the candidate data store. That's where the means to be. It's a little bit irritating that name, if you don't know that story, because it's really copying the running data store into the candidate. That is really good. For whatever reason it's called discard changes. But every implementation might have a candidate data store, so there's a candidate capability. During the hello exchange, the server will say, yeah, I can do candidate. If the server can do candidate, here's the commit operation. You can run a commit, it's just committing, but the real fancy stuff is trying to confirm commit, and that works as follows. If you have multiple devices, they need to get changes applied consistently, all of them, all together. And in between, even the network might stop working. What you do is, you store a candidate data store of all the devices where the changes, and then you do confirm commits on those devices. And what you can do is, confirm commit means the device commits the change, and the management system has to go back and confirm it. So you commit, you try to get back into the device, and you confirm everything is right. If for whatever reason you can't get back to the device is going to roll back to the previous configuration. So it's the automatic rollback that's important. And you can provide a timeout parameter saying, commit this configuration, I'm going to come back to you within a minute. If I don't come back within a minute, you do the rollback. So you can specify a time window. And if for whatever reason the new configuration is not consistent, you essentially have to do nothing. You just wait. And then it's going to be the rolls back to the previous state. That's useful. That's practically useful. It's non-trivial to do it. Actually, it's also not that hard. But it's really, really useful to have. Another operation that comes with the capability is a validate operation. You send your data store validated. That's most useful if you use candidate data store. So you make changes to candidate. You want to know before you actually do a commit, is the stuff that I pushed on actually useful? So can the device validate that according to the device knowledge of what it has in terms of resources and so forth, this is something I can actually commit. It doesn't mean necessarily that commit really succeeds. It's giving you no guarantee that commit really succeeds, but it gives you the warm feeling that at least it's not completely screwed up. Or have references to other things that aren't really defined and stuff like that. That's what you do practically in validation too. Okay. People in the working group came up with extensions already. Some people thought that having a global lock is kind of nice, which means to global lock just means it limits concurrency. Because as more you get locked, global locks established, others can't go into the device and do something that's totally unrelated. So there's an extension for partial lock, which is taking kind of an XPath expression you select the node tab that's being locked, as part of the partial lock, and it returns to you a lock ID, and later on you can use the partial unlock to unlock that partial lock of the table. So the idea is that you customer provision that you might be doing something to devices, but you can restrict it for locking to something that's specific to customer provisioning, but other stuff on the device might still be done without affecting those parts, so you can have two partial locks that can be doing things on the device. So it's just narrowing down the concept of the global lock to smaller portions. If you have a small device, you try to use it here, and if you have something big, that might be used. Another extension that came along was the notion to shift configuration for other notification changes as an event stream. And the model that's being used is you create a subscription to receive notifications. So something initiated from the server towards the client. And the abstraction is you subscribe to a certain stream, you apply a filter to it if you want, and you can specify optionally start and stop time. And the funny part of this approach is that the start time might be in the past. And if the device has local storage of notification data, you can actually restart that's locally stored in the device and let it be straight to you. And everybody who's running the Linux system knows, I go to look in the last 5 minutes and use Taylor to figure out what happened in the last 5 minutes or 10 minutes. This is essentially doing the same thing, because you can just say, give me a subscription from that point to that point, so that's the time spent and let something interesting happen. And so you don't have to grab the whole log. This might be used, but you can actually play the part that's meaningful. Again, that's an addition. Not every NetConf server has to consider it. Okay. Now, time to talk a little bit more about this powerful edit config operation and how it works. So if I want to make changes, I want to add something to the config, I want to remove something from the config, and so on. And the question is, how do I actually tell the server what I want to happen? And the way you do it is to provide an XML diff, if you want. So a portion of XML that says this needs to be added, this needs to be removed, this needs to be changed. And so in the XML that you provide to the device, you have to specify this should be added, this should be removed, this needs to be merged, or whatever you want to do. So you write down for every little piece what should the server do with it. Now this is probably best looked at by looking at an example. So here's a complete RPC message. Now invoking a config, the first argument says I'm changing the running data store, and my target is running. And in the second parameter to the RPC in the config element, I now have config that I ship to the server. And so here in the interfaces element, it sits in a different namespace, there's an interface, and I want to change the MCU from the Ethernet 0/0 interface to 1500. And I want to change this particular instance. I don't want to add immediately. I want to change the property of an existing interface. And so what I'm doing here, I use an attribute, the operation attribute, which has a value of replace, and that says, go into your config, find an interface named Ethernet 0/0. If you found one, change the MCU to 1500. This is going to fail if there is no such interface. If you replace it, the nuclear system, I'm going to change something on that interface. If for whatever reason I'm sending this to the device, you have totally different interface, you need to do anything about Ethernet 0/0, and the device is just going to fail it. And I'm right. If you create or replace, okay, if you create or replace. So don't trust me, read the RC. Or ask any. That's all. But sometimes any and the RC don't agree. So that's also subtree filtering. On the get and get conflict operations, and then you can pass a filter down so that you don't get everything. One way of passing a filter down is if your device supports XPath filtering. You just write down an XPath expression and just say, give me that part of the subtree. That's not mandatory to support. So it's mandatory to support the subtree filtering. And the way it works is you write down kind of XML conflict that acts as a template, selecting everything that's hanging below what you wrote in your XML conflict template. That's the easy way of explaining it. The other way of explaining it is going through the different nodes that make up your subtree filter. And the following slides go through all the details, which I prefer to skip over because that's really something for reading our keys. But what it actually does, you write down something like, here's my interfaces container, and here's an interface. It might even have an attribute that is being filtered. So here's a selection node. So I want to select everything that's on my app stream in there. And I can have content match nodes, but only of interfaces that have a certain type. So you can actually build more complex filter expressions these days. Okay. Getting closer to the end about NetConf itself. Transport, always a fun discussion in the IETF, but we run it over. It was relatively quickly settled here on SSH because operators seem to use SSH a lot, after the CLIs anyway. So using SSH has the advantage that the key material that's on the device can actually be reduced because they're from CLI. SSH has great interesting properties like having multiple independent channels. That's not really used anywhere in the NetConf specification. Probably some implementations make use of it, but it's not really part of anything that's required from the NetConf messaging there. Okay, so we found application layer messages over stream-based transport. So we get back into framing discussion. So we need to mark the end of the message and the beginning of the next message. So the first attempt at returning XML was to have a special marker. That was picked because people believe this particular sequence would never ever be part of a valid XML document. That turned out to be wrong. So NetConf 101 changed that. It actually did something else. So it actually used to chunk encoding. So for those familiar with HTTP, a lot used in HTTP transfers today to send out chunks of data and then the next chunk of data and receive it as the sum of those chunks. Now how does it look on the wire? So this is now really how it appears on the wire. So a session that opens, the server sends hello. So there's the whole hello XML block, and then there's this marker saying this is the end of the first application that That's still the case in NetConf 1.1. And the reason is only after having received the hello, you actually know that there is one in NetConf 1.1 and 1.0. So you have to be backwards compatible, at least for the hello. Now, if client and server, if they both announce to do NetConf 1.1, they change the framing to the new chunk encoding. And then you get something, well, the client also says hello, the same thing. And then they use chunks encoding, and that looks like this on the wire. So you have a magic character and the number that says how many bytes are going to follow, and then there's either more bytes to install another trunk or a special remark of data style visibility, and that's the function that they insert. So here the client is sending one trunk essentially, and here's an example where the server requires using multiple trunks. An initial trunk, and then it sends a trunk for the first interface, for the second interface, and then it sends the final trunk. And the reason taking some time to get the numbers right. But I don't tell you how much white space there is. If I'm off somewhere, it's all just because you're counting a white space is different than my counting the white. Okay. That's the quick rundown of NETCONF. Any questions? So the question was for audio length. So the concurrent commit says if I don't come back within a certain time interval, I'm going to roll back to what I have previously working. The question was, why not do it differently? If you don't come back, you keep the content, but if you come back, you restart because of the conversion. There's a simple reason why it was done this way, because if you do a configuration change that prevents you from coming back, you have no way to tell the device please go back. Right? So if the configuration change cuts off your management system from the device, then either the device detects automatically that it should roll back, or you have to send someone to press a button. So that's why this change. Any other questions concerning NETCONF? Come on. You must be totally confused if you never heard about NETCONF. Good? Good, let me go on. So Yang. It's not an acronym, it actually does not stand for anything. It's just called Yang. So it was created, so discussion started in 2007, and then in 2008 working got established. And then in 2010 Lambda version 1 came along, together with another document that provides a set of data types for IP addresses, MAC addresses, timestamps, and these kind of things. There's another document, guidelines for authors and reviewers. If you want to write again data model, that's strongly suggested that you read it and learn a little bit about how to do things, what to look out for. There's an experimental extension using language abstraction that talks a little bit about abstract data types, kind of an object-oriented way of looking at a data model, that's experimental. There's a mapping document you can map to Disco, so that we let them do Silicon and a couple other stuff. And there's another document that came out recently, which is if you have this module written as an IDT, and you can actually access the content via NETCONF. And this document has what the automatic transformation you get from something that fits in the module space and access it in the NETCONF namespace. And then the information of architecture there. Okay, so what Yang does is data modeling language is used to model configuration in state data. It actually distinguishes between those two items. Manipulated by the NETCONF protocol, it allows you to define new NETCONF operations. If you're saying you need a repeat operation, you can define it. You still have to implement this, of course, so you can define how it would work on the protocol side. You don't have to change the protocol. And you can specify the form of specific NETCONF notification. Yang uses a complex syntax and human readability as highest priority. Well, the idea was that it should be easy to change data module snippets and have humans be able to read what it means. Of course, that's subjective in nature. It's often easy to agree on something that's not readable, but agree on something that is readable or something totally different. So that's up to you to decide at the end. Since the specific code human readable syntax might not make your tools too happy, there's experience or there's Yin or Yang, which is essentially the representation of the Yang data model in an XML statement. So you can stick it into XML processors and keywords and the whole chain to do something useful. Okay, I already said Yang can be translated to XML schema. That's actually not defined, but we have implemented. Defined as a translation to the XML. Schema if you can use actually validate messages before you send them out to the wire. You can make sure that even the client side can validate stuff before it ever hits the server. If there's a configuration management system that's really involved. Okay. Then, for the other concept, for everything starts on as a module, you write down stuff that is fitting to a module. The module has a name, and the module has a namespace. That's the module. So if you retrieve configuration data, then the data models that the device implements, some might be standardized, some might be vendor specific, some might be standardized by someone else. Like an IETF standard, and IETF and vendor specific stuff. And to make sure data never collides, means everything needs to have a proper namespace. So when you write down a Yang module, you give it a name, and you write down this is the namespace that is used to distinguish or to clearly identify whatever is needed in the data. If you write a module, you usually import something that someone else already has written before, like on a data type. So the concept is you import a different module and then you can use stuff that's defined in that namespace. You can also break the module down into so-called submodules. The submodule doesn't have a namespace. The submodule is something that's getting assembled into a module. That's probably not used by any C in the IETF. It seems to be used by some vendors to modularize, have a modular structure of submodules that all get merged into one module logically, into one module. There are lots of working with internal debates about this. So if you want to have a long discussion, you can go and ask the question. Is both of them useful or something like that? To give you an answer. To give you an example, this is the module set up in the metadata of the IETF type module. So we start with the module keyword, and then there's the module name, IETF type, and then there's a solid base. Probably that's not really human friendly, but it's program friendly syntax. And solid base. And after the module definition, the first thing that happens is we become the namespace. So everything that's being defined sits in the namespace, and type. Since that's a long name to remember, you can write down, I usually call it IMA as a prefix. That is a suggested prefix. The point is that if you import something, you import a module and everything that sits in that module namespace. And sometimes you need to refer to stuff in that other module, and then you can use a prefix to give you a nice author indication or referring to something else rather than having rather long name. Okay, metadata, if you ever have looked into the mid module, this is where it's coming from. Organization responsible, some contact information, description clause. Probably could have been an IPR and copyright notice clause, whatever. There's a revision clause that's pretty useful. You can write down this is revision source, so you actually have to write down initial revision, and there's a reference clause as far as this is actually published now, C6021. Not sure whether you still recall the hello exchange, that is D. The hello exchange announces the data models that are being implemented, and it's announcing the revision. So if you talk to the server actually tells you, I'm going to implement this data model and this is the revision that I implement. So you know what to expect. Probing and figuring out what works in the business. Within data types, integers, signed, unsigned, with different bit sizes. There's a decimal data type. There was a long discussion about a 4-bit unit, and let's figure out the decimal to be next. The string data type, enumeration, boolean bits, binary. Binary really means the encoding on the wire is base 64. You probably never have to do that, but it's going to be base 64 if you ever see it that. And then there's a bunch of type data types for references. So sometimes you have an object in the copy that really says, I'm referring to that interface over there. And so the content of this data object is the content of something that exists somewhere else. That's a refresh, so referring to something else in the tree. You can have an identity graph with a reference to an identity, or see later what that is. You can have instance identifiers. And then there's the great entity type that's the equivalent of void and tree. You didn't have anything. Only that was useful or something. The syntax itself, the format, how any data model looks like, and some of the way the base data types work, is kind of an evolution of SMING. SMING was an effort, there was an SMING that we wanted in the IETF that stayed that way, but it still left something that actually was useful. So if you want to define a new data type, so taking again an example of IETF type module, so using some of the metadata out here. The way you do it is to just define a new data type, you use the keyword type there, and you give the new data type a name. So that's my before address here. And then you open another block of statements using curly braces, and then you say that the base data type for this type is string type. And by the way, the string type is constrained by this regular expression. As we all see, that's how you write a regular expression from how you before. If you want to see something really fancy, then look up the regular expression for IDB6 addresses. That's really fast. So compared to that, this is trivial. If you know regular expressions, you know there are plenty or even more different interpretations of what a regular expression is. This is using the regular expression format that's used by the XML schema standard. That is translated to XML schema straightforward. Look at the plus sign. So you can actually break a long string constant into multiple string constants and plus signs in there. So that it fits them out C format. So it will never be published. And there's a plus. You can't copy this way. Here's a type definition for an IP address. So that's my IPv4 address. Here's the IP address. And so here you have the union, and that's the union is by an IPv4 address and IPv6 address. So if you have to write down something that works with both of them, and you just use the IP address data type. There's a description and it says, well, things should be designed such that the format of the string value actually allows you to distinguish between the v4 and the v6 address. That's true for v4 and v6, and I don't know when the 10 comes along, so you need to pay attention that this didn't provide. Okay. So that's just a data type definition, but what we want is actually define how the structure of the data tree looks like. So in the data tree, an element is always going to be in a read. So there's a tree, and at some point in time, there's a read in the tree and have a value. So that's the simplest thing you have at the end of the computer skill. So one value, no further children, and you have exactly one input. In many cases, you have multiple instances. So if you want to model IP addresses assigned to an interface, you might actually have a whole list of IP addresses assigned to the same interface. So you can use a leaf list to model that. And so you have one value in the action element with one value, but no children, or no subtree hanging around that. But you can have multiple instances for multiple IP addresses. Okay, so we have leaves, we have lists of leaves. Now we have to build a container structure, so we use the container data node to say this is just a container somewhere to span a tree and to get the tree community structure. Most of the containers don't really have any meaning except the exceptions. That's what they do. Okay, but so this is just a container to structure something. If you want to model interfaces, then you really have a list of interfaces, and in each case has multiple leaves or leaf lists that actually provide the properties of the interface. Actually, right down here is a list of interfaces, and so it holds no value but a set of related children. You can have multiple instances, and to distinguish those instances, you have to specify which elements have a key property. Okay, examples of how to make this here. So here's a simple leaf. I'm going to model a resolver configuration. So that's part of the operating system that knows to the DNS server to call. So I want to specify the domain. The machine believes the domain. So I'm using a predefined data type. There's a data type called domain name that I'm importing from the module which has the prefix on it. And so that's my shorthand to refer to this really ugly long name. So I'm importing that domain name. I'm setting a property for this data node that this is mandatory to define. So for configuration to be valid, this needs to be there. It's a configuration node. The config tree. That's not state data, that's config data. And then there's a description. So that's the whole thing of the system. Now in the XML serialization, when you ship it over the wire, what you get is a lead XML element called domain, and in there there's something like example of. If you want to model the search list, you resolve those two. Then you actually have a leaf list of domain name extensions that are appended to your name to be resolved. So you can model that using a leaf list, so there's a search list. Again, data type, these are the domain names. Have a description here. And now the important thing is I'm specifying here the order of this list matters. The server is not allowed to reorder the public things in different order as noted. And that's very simple here because that order determines how you, in which order you extend and which order you resolve conflict. So the server needs to preserve the order that was configured and given to the server. Okay, the XML serialization is the step to search element that is the Okay, now I want to put things together. Probably it's useful to have a container, I call it system because I like a better name for it. I say this system container, this part of the XML tree is config tree, and that inherits refer to download, so I don't really have to write complex 2 everywhere. Somewhere up, it says complex 2 is really a complex 2, and if I don't need to say anything, the default is complex 2. Be careful what you do. Also, I have a read host name, that's the name of my system, that's the domain name, and then I have a container resolver which has the resolver domain, the read list of my search. Yes, and if I look at the XML serialization, it says something like this. So this is the container data node, this is the read one instance, this is a read one instance, this is the read list of the instances, and this is yet another container. Okay. Next thing I want to specify is which DNS server am I going to call. So I can have a list of DNS servers I might create in my policy. So I create a list of name servers and I key them by their address. The name server has an address, and I designed here that the setters I can have every address on AWS, probably the name of the for the sake of example. What I would get in the XML representation is the first list element, which has an address in the table, and here's the second list element, which has an address in the table. Okay, that's the basics. Now the interesting stuff. When you do something like this, the first thing you observe is your model, if you try to standardize it, it's not going to model what the vendor really needs to be modeled. So if you define a standard for how to configure IP addresses and interfaces, then the standard likely covers the common things, but not the clear features. So the first thing the vendor likes to do is actually expand the data model. Putting in vendor-specific expansions somewhere there. Even in the standardization, you usually have one version and you later add additional features there. To make that work, there's an augment statement that allows you to say, I'm writing down a little specification of data nodes here, but this should actually pop up in the interface that's defined over there. So you can extend something by providing your own definitions that actually show up somewhere else in the database. That allows you to write vendor-specific extensions to an interface data model, and if someone retrieves everything that's in the interface subtree, that you will get the standardized interface config plus the vendor-specific interface config mapped together, and not some different parts of the interface. So that's really crucial to have. For those who are familiar with SNMP maps also had a way of augmenting tables, but those tables actually ended up totally different in the OIDC. So retrieving them wasn't totally trivial. Another cool feature is the must statement. In your data model, you can write down constraints that need to be satisfied. If the server is being asked to validate the candidate data system, the server is expected to actually check whether these must rules are satisfied. Now that's a sharp tool. It encourages people to over-constrain the data model. So it's very easy to write down must rules that prevent later extensions. So you have to be careful. Think about having an open mind for future extensions. If you are very strict in your must rules, you might later on regret it. So now you want to extend something that actually doesn't work anymore because it's violating must rules. So it's a very sharp tool. Think twice how you use it. Another interesting tool is the when statement. Sometimes you have augmentations that are only valid for certain situations. For instance, you have an extension for Ethernet interfaces that makes sense for all Ethernet interfaces, but not for any other interfaces. So you can write down an augmentation and say, well, formally, this augmentation only is meaningful when the following condition is satisfied. That's tremendously useful. So you can narrow down and have consistency. So someone who is trying to configure VMs is not going to do it on APM interface. So that's useful. Again, in both cases, you use Expath expression to write down the condition. And another interesting feature is the presence container. You might remember that I said the container really has no meaning other than being a container when I was on this slide view. Well, it really doesn't have any meaning unless someone writes down in the container definition this is the presence container, at which point it might carry one bit of information. So the fact that the container is present actually means something to the device, and if it's not there, the device behaves differently. You can argue about this, about the value of this, but it's there. It has an advantage of that it can sometimes be very concise. For instance, if you want to enable something, you just create a container but nothing inside, and everything is defaulted. So you enable SSH by just putting an SSH container. And so it takes complete default config to run an SSH script. It's very concise because the config only says SSH. But it means that people need to understand that this container really is magic, and different than the other containers that are on them, where the container really doesn't mean anything if there's nothing inside. You can actually have this, or you can't have it, doesn't really matter. And so, again, what out for present containers is magic. So any remarks that it really has interesting interaction with the mandatory statement. Remember, I had it in one of the examples. You can say this really needs to be mandatory, and that can actually be inherited downwards. And if you have a package container somewhere in the download, inherited stuff, and those things interact, you might have surprises if you haven't got the specification carefully. Okay, just an example of an augment. So I'm now augmenting my resolver. I want to put in a debug config now. So I'm saying here's a container debug, and I make it a presence container. So the debug container is there, debugging is enabled. So I'll put in here. So I save an explicit need to enable disable, and I say this one bit of information to the presence container. And I have a read, this is a debug level, that can be low, medium, or full, which has a default, and it's non-mandatory. Then I might just write down in my config, here's my system resolver container, and in there I just put in an empty debug container that I'm actually currently debugging. Here's an example for augment and must. So I'm augmenting my system resolver config with additional features. So I want to have an access timeout measured in seconds. So I'm using 30-bit unsigned numbers measured in seconds. I say this is mandatory, maximum time without server response. If that happens, then I want to do something in timeout. Here's a retry timer, again specified in seconds. The period after which to retry operation. Apparently I said retry before timing out. So retrying after timing out is easy. I hope this is not something that's fresh inside your data, but everything that's really easy. So I can write down a constraint here because the value of this read needs to be less than the value of that read over there. And so if someone now configures values that don't satisfy this simple rule, then what happened was I can actually specify what's happening on the protocol level in the RPC error reply. I can actually get a meaningful error established as retry time and invalid, and I might be given a meaningful message that I can see that too. So this is an example when Yang really ties directly into the semantics of last time. But it's extremely useful, just hanging its tails. Would also be useful, but not as good as being able to specify what it actually means to the user on application, this particular type of thing. Here's an augment and when. So I'm augmenting system resolver main server, with a list of main servers that I have. So I would just want to count the number of DNS queries sending responses received. So I put in two reads, transmitted and received, count of 32, they are not conflict, operation is paid apparently. But I only want to have those counters as the main servers actually needed. So I'm checking if the status of system resolver main server status, if that lead for this list instance is enabled, then these counters apply. If I'm having a main server in there which is not enabled, don't expect the counters to be. So that's what you would get in the XML representation. There's more fancy stuff. And I'm not going to go into great details about this. There's a way of grouping definitions together. It's called a grouping because that's the way XML schema calls these kind of things. Probably a better name would have been kind of a template. That you're providing a bunch of definitions that you can reuse in multiple contexts. That is called a grouping. One of the great features is you group something together because that pops up multiple times when you're tired of writing it multiple times. So you just group it together and create a grouping, and then what happens in real life is you reuse that grouping 5 times and the 6th time. It would be slightly different. Yang actually allows you to overwrite the template when you use it. You can say, I'm going to use that grouping, but by the way, you want to use the little thing. So it's more like a template and you see the way and say, oh, that's part of the template, so actually do something slightly different. There's a choice. Great description can be used to provide extensibility to what is that. Sometimes you have different ways of doing things, and you know upfront. What I know now is in 5 years having additional things ways of doing things. So you want to provide an extensibility there. So you make it a choice and you say, well, if that mechanism is used, that's the conflict for that mechanism. If another mechanism is used, that's the conflict for the other mechanism. And that's everything I know or care about today. But later on, someone can go in and take the definition and actually augment something into this course without touching your mouth. So we provided the choice and someone goes in from the side and says, I created this new additional feature to do something, and now I'm augmenting the necessary configuration where it should be. Notifications can be defined in our procedure, and I think I have a sample for this stuff as well. Here's the grouping. I define a new grouping called target, which consists of an IP address and a port number. That is spectacular. I can now change my definition of a main server and say, well, I really want to have a main server which is just using this combination of my server. So I'm really spell that out. I just use the grouping. Now I'm using different keys. It doesn't change anything on the wire. On the wire, it's exceptional. The fact that this is really just something for the data model writer to say cycle. This is simply anything that's used on the wire. The choice. Well, suppose I want to transfer my DNS data in some other place. There might be different ways of running this. I can probably run periodically using a fixed time interval, so I need to specify the length of the time interval. Or I just want to do it daily, so once every 24 hours, at a certain unit of time that I want to specify. Or I want to do it manually, whatever. Or something else that I don't know yet. So this is just a case for choice. If I have a different strategy to distribute and trigger my update, I can just add something into this list, augmenting something into this choice here, have a different case, and then the configuration will get extended. The choice in this case is not visible on the right. So in the configuration, you would either see an XML element called interval, or you would see two XML elements daily and time of the day, or whatever you want to augment in the future. Here's the definition of a notification. Suppose I want to return or send a notification on main server failure. This is how I can do this. I define a notification, main server failure. Have a description, it has a lead, and that's the address that I'm sending when the main server fails. And I'm now using here, I'm not writing down this is a lead of type IP address, because it's not just an IP address, but it's one of the IP addresses that I configured namespace. So I write down this is a lead reference to some other lead, and here's a path expression of the path in the schema tree to reach that particular lead. So it's constraining it to one of the main server IP addresses. So it should be something the main server failure from IP addresses, not on the wire, you would get a message notification, and there's the main server failure with the address, and for all notifications there automatically an event time code so that I would going to be there automatically. If I got the question correct, the question is, how do we rediscover the head of main servers? Well, you probably configure those main servers. So here's the question is, how can I discover the maximum number of main servers that I can configure? Using the data model with conf. You will, however, once you send an edit config, you can figure the one that doesn't fit anymore. The server is going to call you that doesn't work. You can write a data model that actually models that, so you can retrieve the limit that your particular main server can take. But that's not in this model. This model assumes a world where this kind of things never ever exist. So, another example for the RPC, this is how you define your own RPC. Another operation. So you use the RPC keyword, and then here is an activate software image RPC, which takes as input a lead, which is the software image name that you want to activate, and as output is the status, which is the string in this case. And on the wire, what you send is just an RPC, and in there, where you usually have a get config, edit config, whatever, you just have an activate software image RPC that you invoke, which has an image name. Of course, that definition exists in some particular namespace. So even if you would define your own get config, it wouldn't collide, it would fit in a different namespace. You will come to get config and not NETCONF get config, and it will work out. And if you read the NETCONF 1.1 specification, all the NETCONF operations are actually defined in there in 1.1. They can actually go in and see how they work, figured as a template by their own up to definition between that. Okay, questions? More than. Questions about this one? Yeah, but everybody is totally confused. Just to give you an overview of what's happening in the IETF and the network working group, there's a document that's currently working group last call. That's defining a configuration data model just for interfaces, because interfaces are really features. If you can't configure interfaces, then everything else can't be really configured as infrastructure IETF. And the idea was to come up with something that is really the most basic. So, following the principle, you don't can't read anything. So, not particularly. I'm just make sure that we have the priority. This is really just about interfaces. It doesn't even talk about addresses. I come to that later. So maybe an interface really has a name, it has a description, it has a private, it has a location that it can be enabled, disabled. It has an IFN next to it, there's a lot of net keys to refer to interfaces so you can actually link things together. It has an MTU, and you might want to enable stuff. That's essentially it. It can be stacked. If you have questions, this is last call. There's one evening today where you can just go. It's a short document. It's a short document and have an appendix where it shows how this can be extended to normal fancy stuff like VLANs and so on. There's another document which talks about how to configure IP interfaces. So that's not talking about configuring IP addresses and interfaces. People will start. The first time in the IETF, they're trying to build a standard on how to configure an IP address and interface. We're not done yet, so it's in working with that call. It's not just time to celebrate, but no, wait for the second slot. So what's happening here is we're making use of augment. So we're augmenting IP configuration into the interface. And so there's interfaces, and now there's the IP subtree, IPv4 subtree itself, IPv4 enable, disable, forwarding, blah, 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 set of IP addresses. Whether you specify here the case, whether you specify prefix length or IP address in the net mark. Some people convince us that they invite out the use non-configured net mark and then use it further. So we have it here. Again, this document is being last called for this evening. It's short, something to read. Here's the IPv6 version of it. So in IPv6 you really have a prefix length and nothing else. It's good enough. But then you have all these fancy ways of creating temporary addresses and what have you. So that's your auto-configuration stuff. You can configure what type of auto-configured addresses you want. There's another data model that's being last called, but I didn't use until Tuesday for that one, because that's a little bit more complex. That's the data model modeling the core of a routing interface. Again, that's something that didn't exist in the IETF. We have unit models for different routing protocols, but not really how they tie together. This is taking a different approach. It's trying to model how the stuff is being tied together. Not really tremendously useful because extensions need to be written for the different routing protocols. So the model that's behind it is there's the main routing table, there are static routes and direct routes. That's just not the configured in that model. Then there are different routing protocols that interact with the main routing table, or any additional routing tables that you might have. And between the various routing tables and the routing protocols, you can actually use information up and down, and that's controlled by having route tables. That's a very generic model. There needs to be followed with additional data models to always have VPP and whatever people want to use. Probably priorities, but I'm pretty sure this evening we're going to look at this and send something to the network mailing list, and we can look at what exactly the issue is and what it is to use it. Maybe do that. If you can, try to explain the problem well, and then you can see whether or not you need to do anything. Okay, so if you look at the definition after the lengthy work, there's a system data model that's being worked on, which has very interesting operations like system restart and system shutdown, tends to be useful. Set current date and time sometimes also useful. Has very information object, this operation is state here, or what platform, what kind of device am I actually talking to. Talk about time, so how do I set my time, which time zone is the device in, how do I specify the time zone, do I specify a location, like Canada, Vancouver, probably that's just the location in the set, or do I specify UTC time off? Do I use NTT, and if so, what NTT service do I talk about? Again, having people look at this, it is not copy to homework. There's DNS stuff, there's radio stuff, authentication stuff, covering SSH keys, because that's a bundle of those stuff makes sense. And that's about it. So the status of this is we're getting some young data models out of the pipe. Some NETCONF data models have been published. There's a whole network NETCONF access control data model that I didn't talk at all about. But you can actually specify what different users are allowed to do in the NETCONF data store. If that's needed. There's an IPv6 configuration data model sitting in our Subtree ready for reference or whatever. So already. There's work on an SNC configuration data model that still needs to mature a little bit in the network working group. As we hope there are more data models coming out in the future at this time. That is our encourage subject matter experts. We provide OSPF data models. We can do this, but we can provide help. So anybody is considering that useful and has questions, talk to young people, and they will help. Implementation. Nothing here is complete. Probably everything is incorrect. That's still something useful for some people to know. NETCONF implementations, there are various organizations implementing stuff, vendors, open source stuff. The list is not, when I talk about vendors, never ever anything is complete. It's wrong. NETCONF devices, this is a list of vendors that seem to be shipping NETCONF in at least part of their devices, not necessarily in all of them. Sometimes you have to get the latest OS that NETCONF. So that depends a little bit, not to be sure I left all vendors. Young implementation, experts, commercial, open source. You can choose what you like. The common tool that we use the Yang, there's actually a group of people that are the Yang doctors, like we have NIST doctors. If you write something, the recommendation is to use Yang as a tool to check that stuff is correct, or humor is how they then call it. Data models, I mentioned them already. Several things going on in the IETF or the working group. We'd like to see more of that. Other SPOs for other standards organizations, Open Networking Foundation, the specification OS config, which has the data model compiling version on. Sorry? How do I determine which model? Yeah, you either believe vendor documentation, or you open a session and look what the hello tells you. And you hope that that is correct. Cable apps seem to be slowly moving. There's been done lots of follow that and people seem to be interested in getting that transport for their devices. And that's a unit form of TM, and often someone knows none of this is serious. Yeah, there's stuff going on in there. The video of potential to probably skip that. But just for those who think that XML was really the technology of the beginning of the 21st century and we have moved on. So there's a translation of stuff into JSON. This is how it looks.